Thus far in this series, we've talked about the sprinkler database and the K-factor selector. In the K-factor segment, I mentioned that we have two drivers for the starting sprinkler flow. It's a relationship between the opening of the sprinkler, the orifice, the pressure involved, and the resulting flow. They're all related. Here we're going to talk about how sprinkler K-factors, pressures, areas, and densities all relate. We're going to go through the two main drivers, so to speak, for sprinkler flow and look at examples. So talking about flow, when we talk about how much water a sprinkler discharges, it comes down to two basic relationships. The first is the K-factor formula. Q equals K times the square root of P. Q is flow in gallons per minute, K is the sprinkler's K-factor, and P is the pressure in PSI at the sprinkler. This is the relationship we talked about. The opening, the orifice, simply throttles the water as it goes through that opening. A smaller opening or a smaller K-factor means that less water will be able to flow through the opening at the same pressure. If we have less pressure, less water will flow through the opening. The opposite is true. Larger openings mean larger K-factors, and they allow more water to flow through at a same pressure. Higher pressure with the same opening means more water is allowed to flow through. This formula defines the relationship between pressure and flow. For instance, with a 5.6 K-factor sprinkler and 7 psi pressure, the flow is about 14.8 gallons per minute. When I first learned hydraulic calculations, I stopped here. I thought, well, if we have a K 5.6 and need a minimum of 7 pounds, 7 psi, then that's it. That's how the most demanding sprinkler works. But it's not, because there's also a second driver. The second driver comes from NFPA 13's density area method, which looks at how much water per square foot a sprinkler must deliver. What density of water does the sprinkler need to achieve when the water hits the hazard? And how much area is that sprinkler responsible for? What if the sprinkler covers 100 square feet? What if it covers 300 square feet? Flowing 14.8 GPM in either of those cases, on average, would result in completely different densities of water. So that area, the amount of area that sprinkler is covering, affects how much effective density that sprinkler is going to have. And we know from our basic building blocks of fire protection, higher densities of water will be able to cool the fire faster by absorbing much more heat. So let's talk about two drivers that affect the most demanding sprinkler. Whichever demands more will rule the day. That is, whichever factor needs a higher starting pressure will become the driver for that most demanding sprinkler. Let's talk about the two drivers. The first driver is straightforward. Every sprinkler has a K-factor and a minimum pressure requirement. These are usually listed on the sprinkler's manufacturer's datasheet. If a sprinkler has a K-factor of 5.6 and a required minimum pressure of 7 psi, the flow comes out to 14.8 GPM. That's what we said earlier. Different sprinkler types, residential, extended coverage, attic, or storage, have different minimum pressures and K-factors. When we increase the K-factor or pressure, flow increases along a curved line relationship. The pressure-flow relationship is exponential, meaning small increases in pressure can produce larger increases in flow. The second driver comes from the density area approach in NFPA 13. Here, a sprinkler's flow is determined by how much area it protects and what density applies to that area. The equation is also simple. The flow is equal to the density times the area. For example, a sprinkler spaced 15 by 15 feet covers 225 square feet. If the density is 0.10 GPM per square feet, then the sprinkler must flow 22.5 gallons per minute. Now, compare that to 14.8 GPM that we calculated earlier using the K-factor and pressure. Since 22.5 GPM is higher, the sprinkler must actually deliver 22.5 GPM, not 14.8. So working backwards, knowing our relationship, we can calculate how much pressure we need at that sprinkler in order to deliver 22.5 GPM. We can work the relationship any direction we want, forward or back. To get 22.5 GPM out of a 5.6 K-factor sprinkler, we would need 16.1 psi. That's the example we talked about earlier in our K-factor selector. 16.1 psi is more than double the 7 psi that we started with. This means that the sprinkler is density driven, so to speak. The required flow comes from the density formula, not the minimum pressure of 7 psi at the sprinkler. We can graph this and make it visual and more complicated just for fun. The upward curve here shows us the hydraulic relationship, with flow along the x-axis at the bottom and the pressure of the sprinkler going vertical on the y-axis. In orange, we see our first driver, the sprinkler-driven flow. This is the flow equals K times the square root of P relationship. It's the flow from the K-factor and minimum pressure. In blue, we see the density-driven flow. That's the second driver, which is the coverage area of the sprinkler multiplied by the density. So whichever of these two drivers demands more flow rules. Our K5.6 at 7 psi, covering 225 square feet, and light hazard 0.10 GPM per square foot density is density-driven. We need 22.5 gallons per minute at a pressure of 16.1 psi. If we were to use our K-factor selector and we step up our K-factor to say 8.0, look at how the graph responds. We're still driven by the density at 22.5 GPM, but the pressure needed to achieve that comes way, way down from 16.1 psi. So I tend to use this tool less than our K-factor selector, simply because I prefer the output format of that K-factor selector. It's a little bit easier to see results from a whole range of K-factors. But this tool highlights the relationship between K-factor, pressure, coverage area, and density. As a learning tool, it's somewhat helpful to see what's going on with our most demanding sprinkler. So I might personally experiment with this a few times to get a grasp on what's going on, understand the relationship, but then set this tool aside and use the K-factor selector more regularly. So in this series, we covered 3 tools: the sprinkler database, the K-factor selector, and the sprinkler flow tool. We looked at how sprinkler flow can be driven either by the sprinkler's K-factor and pressure, or by the density and area that the sprinkler covers. Whichever demands the greater flow for the sprinkler becomes the driver. This is part of our Meyer Fire Tool Kit, and along with the other tools in the toolkit, is all included at no additional cost with Meyer Fire University. Next, we'll run a few learning challenges and wrap up this series. The next in line are more everyday use tools for the toolkit for sprinkler layout. I'm Joe Meyer. This is Meyer Fire University.
This has been a preview of Meyer Fire University. Join the next generation of fire protection experts at www.meyerfireuniversity.com.